It's pending. Just a sec. Okay, now we're recording. All right. So here we are, week 5.
Keaton, do we have an attendance link?
Oh yeah. I didn't see one get thrown in the Slack, so I'll just create one myself. How fast can I log in? All right. The link is in the chat. There you go. But yeah, machining processes. So we're no longer talking about the theoretical design in CAD, but really how we turn that into reality. So when you get down to how you're going to make something, it's really important that you keep in mind what tools you have at your disposal, because we're not going to just mold this thing in our mind perfectly out of metal. You have to take a either stock or something and cut out of it to create what you want. And so, of course, we're limited by what we have in our shop. You can outsource if something is a little bit above our pay grade. So heat treatment we get done on some of our BattleBots weapons. I know RoboCup definitely outsources a lot of their parts because they
almost everything.
Yeah, you guys make like several bots, and they're very like down to the wire. They got to be up to form, right?
Yeah, like we have a size limit, and so like every every unit volume matters when it comes to putting in circuits and wires and stuff.
Yeah.
And a lot of delicate parts as well.
And then I know hockey, we got our ring chassis outsourced because that was a whole like super complicated process that we didn't even have the machining tools for. But that actually came in like last week and it looks really cool. But yeah, so keeping in mind what you can actually do in the shop is really important. Going from the left here, we have a vertical bandsaw. So there's actually an oval type serrated band that gets rotated very quickly on that machine on the left there. And you would just drive some part into that. The middle one, I believe, is a sandblasting cabinet. I've never used that myself, but I think it's for cleaning, right? Does that sound right?
Yeah, for like surface finishing.
Surface finishing. And then the right tool there is a horizontal bandsaw, where rather than driving the part in, you slowly drop this serrated band while it's spinning onto your part. Very useful. As you can see, you can cut even circular stock with that. Next up are the big ones, at least as far as I've experienced. From the left, we've got the mill, right? So that'll take some tool held in the spindle up there, like the overarching part. Spin that very rapidly, and you drive your part into it on the XY plane with that table on the bottom there, the gray part. And then the lathe in the middle, that takes your part instead and spins your part very rapidly and drives a number of tools into your spinning part to get radially symmetric cuts taken out of it. And you'll see examples of that later. And then on the right, we have the water jet. Basically, just going to take water with some grit added to it and just blast it really hard stock to cut out an up and down profile. Basically a water laser. You get some interesting issues though with the water jet, and we'll address those in a bit because it's not perfect. And then CMA, in the CMA, these a little bit more advanced machines, these take a lot of the manual bit out of it, where you're no longer guiding it by hand. Instead, you're programming what you want the machine to do, whether it's the lathe or the mill. And once you've done all the programming ahead of time, you just load up your parts, zero it, and then hit go, and it does it all for you. Really slick. You can get some really cool geometries out of this. It just has like a barrier to entry because you have to learn the software to program these ahead of time. We got YouTube videos that actually show these in action. Now let me go ahead and now that's going to be an issue. Let me really quickly fix my presentation style. So I'm going to present this entire screen. Yeah. Okay. You guys can see this video, right?
Yep, we can see it.
Yeah.
Sweet. So this is a mill. This one is automated, right? So there's no way someone's doing this by hand. But basically you can see the part or the tool is being spun and driven into the part, taking off progressively more layers, whether it's vertically or in the XY plane. You can watch more of this on your own time. It is very satisfying to watch. Oh my gosh. It's like there's like this perfect like level. Yeah. Lathe. Oh man, you're just gonna default to that window this whole time, aren't you? All right. The lathe, let's skip to something more relevant. Here we go. So it's not really obvious because it's moving so fast, but you're spinning the part and driving a blade into it to get these radially concentric cuts. Really slick for anything circular or made out of rod stock. Let's see here. You can even drive at it from a face to cut off from on the radial or on the axis. And then we've got a water jet. So as you can see, super high pressure water, and it just cuts right through that that stock. Now you're not going to get any more complex geometries out of this other than a 2D profile, but it's very useful as a starting point. And then here is, in my opinion, the coolest one out of them all. 5-axis. Let's see here. Here we go. So just like a normal mill, it spins the tool, but it's able to get all these complex angles for machining the part, that you can get all these like super cool geometries all in the same machine rather than having to change manually how the part is attached. Super slick. Definitely a huge barrier to entry to learn how to program one of these, or just use the software to the software to create the program for these. But if you know how to use it, you can definitely just about create anything. But yeah, so let's take a deep dive into milling. I don't know how much experience you guys have, but just looking at this slide, you can see a lot of common tools we use in the mill. On the left here, you get some end mills. Basically, you can do the same operations we saw in the video of passing it over a part and taking off swaths of metal. On the top right up there, you can see on the left side of the plus sign there, a pilot hole driller. Basically, you don't want to just drive into flat metal with a drill. You want to give it a little starting hole so it doesn't dance around. And so you follow up with one of the drills to make holes. And then I have not used that middle tool there. I don't know, have Sean, Kyle, have any of you used something like that?
The facing tool?
For the facing tool, yeah?
Yeah, I think I faced something for battle bots. It just takes a large piece of stock and removes like a large portion at once.
Okay,
I've done it in my undergrad, which is a while ago.
sweet.
Yeah.
So does it operate basically like an end mill, but for larger amounts of material?
Mhm.
Yeah.
Okay, sweet. I think Valkyrie had to use one of these for their weapon. I wasn't there for that machining, but we had a large chunk of stock that we had to make, like I think a quarter of an inch
Yes.
thinner.
Yes,
uh,
I remember that.
that
Usually
was a whole
facings
debacle.
do not remove that much material.
Yeah, and that was out of steel. Like maybe you could have gotten away with that if it was aluminum. Nah.
Yeah, I do remember that.
All right. So common operations on the mill. You got facing, right? Face milling. These two are going to be used with end mills, or a face mill for the second one. That's just going to be a specialized form of end mill there. Drilling. So whether it's a clearance or a tap hole, just adding that to your part. Pocketing. As you can see, that circular pocket on the part to the right. Or tapping. Now tapping is a little hairy when it comes to the mill, because normally you can just spin it up at a certain speed and accommodate for that by moving the table slower. But with tapping, the speed of your part, or the speed of your tool, has to be carefully calculated, as well as the descent rate, so how fast you push your tool down, so that the tapped threads are the correct length apart and that they actually get done correctly. A little bit more involved than the rest of these processes. So let's talk about the geometry of the actual tool. So just looking at the example tool on the top right, there are two flutes. The flutes you can see are just the curved peaks, if you will. They come in a variety of different types, whether it's 2 or up to 6 flutes. The type of flute or the number of flutes you use is actually very important, depending on what material you're cutting into, as well as how fast you're spinning the tool. There's a link there for some like stats on end mills. You can look that on your own time. It's here. Yeah, there we go. So when you're cutting into aluminum, you typically want to use 2 flutes. So just like the part you see in this slide, or the tool you see in this slide. Whereas with steel, you want 4 or more. The reasoning behind this is if you were to use something like 4 flutes on an aluminum part, aluminum has a much lower melting point, and so you could actually end up melting the metal as you come in contact with it to cut it, and it will end up melting like onto the tool, and you'll see it gum up at the bottom of your flutes. Whereas with steel, you can get away with more flutes, and actually you also want more flutes because it's a harder material, and it puts less strain on an individual flute. The material for the actual end mill varies depending on what you're cutting into. You can get away with HSS, which I don't know what that stands for off the top of my head. I don't know if you know, Kyle.
High-speed steel.
That's
What was
good.
that?
High speed steel.
High-speed steel, or carbide with aluminum. Whereas if you're cutting into steel, you're definitely just going to want carbide. And then the coating on top of that material will actually like dictate the color of the end mill. You can tell just by really looking at the end mill what you're dealing with, if it's going to stand up to your part. The coating is pretty important because it changes I believe it's thermodynamic properties of the tool. So with titanium aluminum nitride or nitrate, I think it's nitride. You want that for steel because it won't pick up heat as much. Whereas just with titanium nitride, you'll just use that for aluminum. Or sometimes, I believe with cheaper parts or cheaper tools, you can just not use any coating. Going back to the why on that, once again, you need space between those flutes for the aluminum. It's going to flake much more than steel would. And so if you have a bunch of flutes, then you can imagine the space between the flutes is going to be less. And so there won't be as much room for the flakes to get out. Carbide is more rigid than HSS, which is why it's necessary for steel. Whereas with aluminum, you can get away with using SSA or HSS. It'll make it a cheaper part, and you'll still stand up to aluminum. The coatings, like I said earlier, allow you to just focus on actually cutting the material rather than having any other unwanted interactions with it. So the part's going to heat up, obviously, as you cut into it. You're making several contacts very rapidly. You don't want that to transfer to the end mill while you're machining. If your actual tool gets heated up, then you could have issues. And then the titanium aluminum nitride cannot be used with aluminum because the aluminum will actually like stick to that coating. And then like you're not cutting anymore, you're running into other issues. Next up, we got climb versus conventional. Now, this is something you may hear a bunch of times. And to this day, when I hear it, I still have to like kind of like in my mind imagine the mill cutting into a material and like move my hands along with it to make sure I'm saying the right one. But if you can imagine in the diagram, right, that I'm going to say orange, that is orange, right? That orange material is being dropped from top to bottom, and the tool is being rotated clockwise. So the flute is going to begin cutting on the further left side and then continue up through the material until it exits at the right side of the material. That's conventional milling, as opposed to climb milling, where once again the material is being dropped from top to bottom, but the flute begins cutting at the outside edge of the material and climbs into the material exiting on the further edge to the right. Now, you don't want to climb mill on manual mills, at least the older ones, because they weren't designed for it. It puts extra strain on the tool itself, and if they're not designed to accommodate for that strain, you could end up breaking the machine or at least the tool. Nowadays, I believe most modern mills can accommodate for climb milling, and there is a difference between the finish of your part. So if you conventional mill rather than climb milling, you could end up with a glossier finish on your part. That's just all. That all depends on what you're trying to use your part for. So continue to talk about pros and cons of the two. Conventional gives you a worse finish, but you can be more precise because you're not going to be pushing into your tool like you would with climb. It's easier on the machine, so you can get down to the exact measurement you want to. Climb's going to reduce tool and machine wear and has a better finish, so you can actually see the difference between a climb and a conventional milling job. But it's going to be less precise because you're pushing into your tool, and so it's going to deflect a little bit. Deflection, if you can imagine, the tool's being held at one end, and it's being pushed on by the other end. If you have a longer end mill, it's going to bend a little bit more than a shorter one. So you'll have less precision with longer end mills. And the same goes for whether they're thin or thick. You can imagine a thin one could deflect more than a thick one. So why should you CAM/CNC? Well, I mean, just looking at the parts available to you on the right, you can make a lot of really cool things all on one machine. Also, doing that by hand, like eyeballing it and if you can imagine the way you move a table manually is kind of like an Etch-a-Sketch. It's really hard to even make circles on Etch-a-Sketches, much less a lot of the arcs you can see on those parts over there. So CNC is really just going to do all that for you. And machine-aided arcs are probably going to be better than what you can do on the Etch-a-Sketch controls. There's less human error, so as long as you program it correctly, it's going to do it correctly within the bounds of the machine's tolerance. And it's a lot quicker to manufacture repeated stuff, right? So like I said before, there's an investment you have to do in programming this. It does take time. You have to map out all the different operations. But if you're going to do it several times, you only have to make that investment once to create the program to machine whatever part it is. But once you've done that, you can repeat that manufacturing process several times with the same program. So let's talk about drilling now. As you can see on that drill on the right, it is not center cutting. It's got a flat nose, which means if you drive that into a flat piece of metal, it doesn't know what to do. It's just going to be rubbing that flat face against another flat face. And if you keep applying pressure top down, you'll either deflect the drill to the right or it'll dance around. You'll see it dance, which we don't want that, because at that point, you're not getting a precise hole, which is why you'll probably want to give it a pilot hole. Pilot holes are little kind of starter holes. As I pointed out the tool earlier, it's just meant to give a little divot big enough so that the drill can begin cutting with its actual flutes. The pilot hole should be the same diameter as the core of the screw you're going to put in that hole. Now that's mainly for if you're going to be driving a screw into it. But the idea remains the pilot hole's diameter should be large enough so that the actual drill can begin cutting. And once it gets started, it doesn't need any more assistance. You can just drive that into the part. At least with wood and softer materials like that, driving a screw in to a pilot hole is much easier than actually just trying to create the hole from the get-go, which allows the threads to actually enter the material and get a good hold. So when it comes to tapping, let's say we've already made the hole on the mill. Now we want to actually add threads in there so we can add a bolt of some sort. There's several options available to you actually. First, you want to decide what your hole size is and the actual screw that's going to end up going in there. Cutting taps cut the threads into the hole. Right, so you're driving that in there, it's going to cut out the wall to make room for those threads. Whereas forming taps push material away from where it is to create those threads. So looking at the graphics on the right, the spiral flute is actually going to push those chips it generates up and out of the hole, whereas the spiral point will push the chips downwards. The majority of the taps, of our taps at least, are spiral point, just because they're the strongest. And you'll see running into issues where if you're not really careful tapping, you can end up breaking a tap, which not only breaks one of the tools we have available, but also you end up with half of this tap stuck in your hole. You can't necessarily use that hole afterwards. So you can see now why having a stronger tap is worth it, even if there are other downsides. There's 3 different styles, at least for the thread end of the tap. Taper is going to cut threads the best, but as you can see, the bottom threads, or at least on this graphic, the top end of the tapping tool isn't actually going to be cutting anything. So you can't really use those bottom threads for your bolt. bottom taps are going to be super hard to use. They're going to fight you all the way down, but you can actually use those bottom threads. So common strategy would be to start with a taper tap, finish off your hole, and then switch out to a bottom tap and give it a finishing touch there to get those bottom threads done. Some tips, you're going to chamfer the hole before tapping it. If the hole was made by a water jet, drill it out. We'll talk later about the water jet, but the holes it makes are not perfect. And so you'll want to make sure those are the actual size you want before tapping them. Smaller taps are going to break easier, whereas larger ones require more force. That's a little bit common, a little bit of common sense, but yeah, if it's smaller, you're going to feel like you can tap it faster, but you're not going to want to do that because you'll probably just end up breaking your tap in the part, which, depending on the part, could require you to restart it. 440s to 1/4 inch 20 is the sweet spot for aluminum. Yeah, we broke 6 440 taps, and I'm gonna say it was a 3-pound program alone, because I don't know. Yeah, it's a big thing every year, because we have all these new members using 440 taps, which aren't the thickest of taps, and so they're kind of easy to break. And yeah, all the holes mainly on a 3-pound bot are 440s. So with those smaller taps, you really want to make sure you take your time and ease it in there. You could like screw it in a couple times and then screw it out, back it out, just to make sure you're not putting too much stress on that tap. And as far as placing your holes that should be tapped, you want to keep a radius of your tap on either side of the hole. Now that means if I punch a hole in a piece of paper, there should be a radius distance between the edge of the hole and the edge of the paper. And I've just apply that to some part, whether it's an aluminum block or something. Now the concern there is you don't want to tap into it and have it cut out regions around the hole that will place the edge of the part too close to your hole, which will make it easier to rip out if you're putting too much strain on the bolt or whatever fastener you have there. And it's also just a good rule of thumb for structural stability. So now we'll be talking about the lathe. So this is the tool from before where you spun your part really fast and drove tools into it. Here you can see a good graphic showing all the many different tools you can use on the lathe, as well as the actual operations you can get done on it. Like that facing operation you can see in the middle there. You could see that being used to create like a pulley of some sorts. You can actually thread rod stock on a lathe. Once again, you can be running into issues where you want to make sure the speed of your tool or the speed of the part is just right, as well as the speed at which you drive your tool into the part to actually get the correct thread distance. Little hard, but there's some functionality on the lathes that will help you out with that. Or you can just go and use a die and play it safe. If you're going to part a part on the lathe, you're effectively cutting a groove into it until you've cut through the entire diameter of the part and it falls off. So that's typically what you do at the end of a machining process. Once you've already done all your other operations on it, you can part it off, and then you have the standalone part and the rest of the stock behind it. Facing, you just cut perpendicular to the axis, creating a flat face on the part. Now, because the part's spinning, you really just drive the tool, if you're looking at the diagram, from like bottom to top, and it'll cut those concentric circles for you. Typically, every part you do, you have to face it just because stock isn't perfect, and you want to make sure all your dimensions are what you expect them to be. Turning allows you to reduce the radius of the part. This is somewhat similar to facing, but as you can see here, you can get some more complex geometries done. Also, you can do this as a precursor to other operations. If you say, like, if the stock is too large for the part you want, you turn it down to the diameter you want, and then continue on from there. Now we'll be talking about the water jet.
Well, you see, the alternative that was the #1 choice is
that's
Juan has joined us for our mechanical meeting.
Hello, Juan.
What's up, Juan?
But yeah, so for the water jet,
Oh, hey, Ron.
it's not manual. You do have to give it some
Okay.
instructions for it to give you what you want. So in this case, we use DXF files. Very easy to create in the Inventor software. And actually, I believe that's either next week or the CAD guide for this week. But yeah, you create your DXF for some drawing you've made. You give that to the water jet, and the water jet cuts out that geometric pattern on whatever stock you've put in there. It's got some limitations based on just the physics of what you're doing. So of course, people, whether you actually create the DXF correctly and incorporate the correct tolerances. Even though it's metal, it is somewhat elastic, and so you can get some interesting dynamics there. And of course, if the tool isn't properly maintained or you don't set it up correctly, you could get some unwanted variances there. And then, of course, if you don't calibrate it or it hasn't been calibrated recently, you can get some error there. But the big one is tapers. Specifically, this is a water jet problem. So if you can imagine a hose that you are covering up the aperture in some way to like make it high pressure, the water spreads out the further it gets from your hose. The same thing happens with the water jet, where if you put the water jet at the top of some metal plate, it will shoot out at a high pressure at the top, cut through your part, but also gradually expand outwards as it reaches the bottom of the part. And so the cut at the top of the plate will not be the same as the cut at the bottom of the plate. And so you won't get like perfect 90-degree angles on parts cut out of a water jet, which could be an issue depending on what you're trying to do with those edges. Also could be an issue if you're expecting some exact length or width of the part. And then going back to the holes, if you're cutting out a clearance hole for a screw, or better yet, a tapped hole for a screw, and you expect some 0.4-inch diameter on the hole, you may get that 0.4-inch diameter on the top of the plate, but you won't get that on the bottom of the plate because of that taper. So that's something to keep in mind as you create these DXFs and as you consider using a water jet for a part. So tolerancing comes down to the idea that we won't be able to perfectly make every part, and it also determines how parts will interact with each other once you've assembled them. So a good example of this is a bearing, which you'll see its fit in a second here. But a bearing, as you can imagine, is designed to sit almost perfectly in some hole, and machining that hole is very difficult if you don't tolerance it correctly. A couple of the fits that you'll generally see. Clearance fit, basically there's very little interaction, if at all. You get two different types there. I don't typically see those myself, the sliding fit and the running fit, but that's just subcategories of clearance fit. Transition fits, so these are going to be a little bit closer, a little tighter fit. Those are going to have to work to put them in there, but once you get them in there, they're pretty good. Interference fit, now these are going to be your press fits. This is what you're going to see with the bearings. where the diameter of the part and the diameter of the hole you're putting it in there, and these don't necessarily have to be circular, but it's easy to think of it in circular manner. The diameters of those two things almost seem to overlap to a degree. And so when you force them to join, you're actually putting it into an almost elastic state where it's held in simply by the fact that it's already in there. And so with a bearing, you can imagine once it's already in a hole, you don't want it to slide in and out. You want it to stay constrained to that hole. By press fitting it there, you achieve that. And actually, yeah, we'll see an example of that in a couple of slides here. But yeah, this clearance fits. You move freely. There's a gap between the parts. They're just basically hanging out. Interference, kind of got to work to put it there. Technically, their diameters overlap, whereas the transition zone, they definitely overlap, and you really got to put it in there. Or no, the other way around. Transitions fit is they kind of overlap. You kind of got to put a little bit of force, whereas the interference ones, you really got to put force in there. And once it's in there, it's in there. And here's a good graphic to visualize that. So looking at so looking at the holes in the shafts, you can see with the clearance one, the black line dictating the outside of the part is clearly below the black line of the hole. Whereas with transition, they're kind of overlapping. There's a little bit of overlap there. And so you can imagine it's going to take a little bit of work to put that in there. Whereas the interference one, that is definitely too big, but it's not too big where you can't put it in there with some force or some mechanical advantage. There's calculators, of course, for everything in here. Here's one for the fit. I basically just tell it, hey, what's the diameter of the part, and it'll tell you the diameter that you need to make the hole for a given fit that you want to achieve, whether it's clearance, transition, or interference. External threads. Now these are kind of fun. My 3-pound group actually had to do one of these last year for their weapon shaft. There's a whole thing, but effectively you do the same thing as a tap, but instead of tapping a hole, you're tapping some shaft that will go into a tapped hole. These external threads are done with a die. You can see the thing with the three circles on it. That's the die. It's not super common. Typically, you'll just buy something that's already threaded, or just use a bolt. In the case of my 3-pounders, we had a weapon shaft that we just bought straight up steel stock for. And we had to put a nut on one end of it. Actually, a nut on both ends of it. So we had to die both ends of it. But yeah, it was a whole thing. So with all the tools I've mentioned so far, here's some typical tolerances you can expect to get out of them. So that's 5 thou on the manual mill, 5/1000ths of an inch. Anything bigger than that is better, typically because the manual mill's like digital readout doesn't even go more accurate than that. The lathe, the same thing. The CNC mill, you're going to get a little bit better. It's a more high precision machine. You actually need to measure your tool as well to make sure you have those variances accounted for as well. And it's as perfect as you're going to get, at least with 99% of the machines you see. Water jets, this is a crapshoot because it also depends on how thick your part is, right? So if you have this huge, let's say 1-2 inch part, the taper on the other end of that is going to be horrific compared to an 1/8 inch plate. So really, your mileage may vary. It's also the worst surface finish. So all just comes down to what are you trying to do and picking the right tool for the job. So shafts, pulleys, circular things like that, they've got some kind of rotational symmetry. You want to go for the lathe. Water jet, you've got some 2D profile that you can create at first pass. So we're talking like maybe chassis plates, basically anything that's going to be rectangular or square in some way. And then the mill, you're trying to make a transitional or interference fit. You can do those like bearing seats on those. Multiple faced features. So if you can imagine those other parts, you have to go at it from different angles and cut off material in different ways to get the desired part. A mill is going to be the best way for that because you can constrain it either on its side or on its back. Then you can tighten that in there and then cut out what you need. Whereas with like the lathe, you really just have the one axis you can cut on, and then otherwise you got to use a different tool. No one's 100% an expert on everything. So if you're ever unsure about something or curious about something, really just drop a question in the Mechanical AMA channel or the shop channel. We got a lot of old people here who have screwed up or learned enough where if you ask something in there, you're likely to get an answer. So now it's time for the Kahoot. I'm gonna pull that up on the stream. Let's see here. Yeah, I'll stop streaming for a second. If you guys have any questions, go ahead and drop that in the mechanical team or the Teams chat there.
That's a pretty baller wallpaper.
Pretty baller what?
Wallpaper you got?
Oh, you see the gin, yeah.
Yeah.
Yep, that is League of Legends, if any of you don't know what that is. Uh-oh. Oh, geez. Yeah, it logged me out in the background, so I gotta go all the way back to the Kahoot.
Obliterated.
Oh, Firefox prevented to pop up. There we go. All right, the code's up now. Oh man, that's 7 digits. That's weird.
That's a big one. Oh, it's Halloween themed too. Look at the jack-o'-lanterns.
Ooh, yeah.
Oh, yeah. Yep. Boo. This 2021 rubber band's made of steel. What the hell? Let's see, we got 8. That might be everyone. How many people are on the call? 11 minus the 3.
Yeah,
Yeah,
there's
that's
8.
8.
Yeah.
All right. Get started. What type of tap do you use to make threads at the bottom of a hole? Bottoming. Let's go. Yep, taper one was really easy to use, but didn't necessarily make tap or threads at the bottom. How many flutes should an end mill have for steel? Four, that's right. You want more flutes for steel, so you put less strain on each flute.
You scared me. That picture had 3 flutes.
Oh, so 3 would be better than at least like 1 or 2. But if you can, 4 plus is the best there. Also, I don't know if I bet we have some 3 flutes in the shop. It's got some movement here. Which tool do you use for this part? Looks like a lead of some sort. Yep, lathe. It's got radial symmetry, or rotational symmetry, so it'd definitely be pretty easy to do on a lathe. Let's go. What is this operation called?
Everything in this class is bad. Is that not complaining?
So this is on a lathe. You're driving your tool into it. Looks like you're removing the back end of some rod stock. Facing. So you'll want to be you'll want to face just about every part you make, just so you get an actual smooth, consistent finish one into your part, and that allows you to get a real good 0 for doing your other operations. True or false? This is climb milling. So we've got the feed. The tool is moving to the left, so the material is going to the right. It's moving counterclockwise, so the flute enters the top of the material first and exits through the bottom back. Is this climb milling? Yes, it is. Climb milling, think of it, it's climbing up the material. At least that's the only way I can remember it. No movement on the leaderboards. What operation is this? This big old tool taking off a large amount of material. This is, I'm not going to say what tool it is yet. Yep, face milling. So really just taking off a majority of a face with a single tool there. Pocketing you typically use, or you typically do with a smaller end mill. You can get better precision on your pockets there. A little bit. What machine is this? All right, the image is a little grainy. You can see in some way something drops onto something else.
No.
This tool's probably got to be like one of my most spooky tools in the shop. Where every time I use it, I'm like, okay, I gotta be really careful. It feels like something out of Saw. But yeah, it is horizontal bandsaw. What machine is this? So the left part there is just a computer. Typically you just plug a USB into that with some kind of program on it. I guess the text on the image kind of gives a little bit of it away. But yep, that is a water jet. You can tell it's a water jet because they usually have those like accordion style like crossbars. I can show the media again. Yeah, so like the accordion style crossbars where it can shift left and right. And really just look for that nozzle there. The nozzle is where the water combined with the garnet is going to be pushed out. That red capsule on the side there is the garnet itself. You'll typically fill that up a couple times when you use not a couple times, but you may have to fill that up when you use the water jet just to make sure it's above a certain level. No movement this round. When should you use the CNC or a CNC? Yep, unusual geometry. If you ask Nikolai on BattleBots, he'll say always. Yeah, that man loves him some CNC Haas.
Yep.
Oh, man.
Nicholas also has the same answer here in chat.
Which materials can you use titanium, aluminum nitride, and mill on? Not to be confused with titanium nitride. Steel. Now, I'm no MSc, but I figure something to do with aluminum being in that alloy gives it an affinity for aluminum, which you don't want when you're cutting into parts with it. Whereas with steel, you can get away with using titanium aluminum nitride. If I want my parts to stay stuck together, I use what? We'll really see what's going on here, depending on how many people choose green. Interference fit. As much as I would love to just glue all my parts together, interference fit will give you a more dependable mate between two parts. Whereas Loctite you'll want to use in addition to something else. What is pocketing? Cutting a shape into the inside of your part. Typically I'll see this done for like seats for motors. But yeah, normally is circular pockets. A lot of the mills in the shop have the capability to like automate pockets for you. You can give it a center point and a radius and it'll do it for you. That's not the same thing as like a CNC Haas. CNC Haas, you're gonna have to G-code it beforehand with Inventor's AutoCAD.
Oh, wow. Okay, I died real fast.
And the last question, who do you contact when you break a tool? The names may change, but the position is the same.
Wait, we still have Kristaps listed as treasurer?
Yep, always contact the shop manager. You won't get in trouble. It's normal for tools to break. We want to make sure we know when it happens so that we can order a replacement. Like I said before, we broke like a ton of 440 taps in the 3-pound program last year. No one got like in trouble for that. We just needed to know when they broke so we could order more, make sure we actually had 440 taps for any other group that needed to use them. leading up to Motorama, it's super hectic. You're just trying to like speed through your bot, and if there's no 440 taps in the shop, and you find out like on the deadline, oh, we don't have any taps because no one told the shop manager, that's kind of an issue. So yeah, just let VJ know. Just drop a link in the shop channel, and you're all good. 12 out of 13. 12 out of 13. Let's go. I wonder what question did it. But yeah, good job, guys. I think
Heck yeah.
go through the CAD guide, right?
Guys.
Yeah. Just to
Gotcha.
mention that it's different this week.
Oh, what was that, Kyle?
It's different this week a little bit, so just to walk through it.
Oh,
All right. Just go through the doc, right?
Yeah, just to give
Yeah.
them an idea of what. Yeah, you got it.
All right. So this week, like Kyle was saying, it's gonna be a little different. You guys can all see the doc, right?
Yeah, can you zoom in a little bit for us?
Yeah. Here's 200. Yeah, 200.
Awesome. Thank you very much.
All right, sweet. So in this week, we're going to give you a little bit more of a scenario. It's not going to be as abstract as the other weeks. Basically, you have a customer. You need some protective shielding for the motor to prevent internal wiring from interfering with an outrider. You see this a lot, at least in BattleBots. We've got outriders for weapons and whatnot. And if wires touch motors, that's a big no-no. So here, we give you some dimensions for the actual part in the best way we can verbally. And here is the basic visualization for the part. Yeah, here we go. So top-down view, it's basically a half pipe, where if you're looking at it like this is from the side view. It's some wall that comes up in a U fashion. And at the corners of the wall, you've got tabs that come out for screws. And at the tip, you have a tab for another screw. And yeah, so what you'll probably want to end up doing is creating that first wall geometry for the half pipe, right? Some kind of arc drawing, extrude that up, and then off of that part, or off that feature, create those two tabs. And this is actually a real part. I know because I designed this part, but you also want to make sure these holes are based off of some screw standard, a clearance hole for, let's say, a 440, or it should say in the oh, well, just make it based off of some screw standard. And actually, do any of you have any questions? Is this confusing in any way? I can answer those questions now. I think that's more effective than just rattling off different features of it. Does it make sense what this part should look like based off of these two figures? I'm gonna take the silence as a yes.
Yeah, I don't think there are any questions right now, at least.
Okay. Now this one is a little bit more complicated, so if you guys run into any issues or it's confusing in any way, just drop a question in the Slack, and one of us will get back to you on that. But yeah, this is the half pipe. this is more akin to what you would be doing in a team, where you have some need and some maybe drawings, some idea of what you want, and then you CAD it based off of that, rather than what we've been doing before with following guides and whatnot. But yeah, other than that, if there's no more questions, I think we call it there, right?
Yep.
Yep.
Sweet. Well, I'll see you guys next week.
He plays with the trackpad.
Yeah. Welcome on to the training.
Again, yeah. What's up, dude? He plays with the trackpad.
He is currently playing Valorant.
Oh, so he was doing a little bit of a burn.
My man. We got